So the idea for this last exercise is to take all of these different things we've done today with Google Earth Engine, working with sort of low resolution data, climate data, rainfall data, these kind of things, and try to do something much more high resolution and specific. So this goes back to some of the data I showed in my original talk, looking at changes in water temperature and water sediment content throughout high mountain Asia. And to do that, you can't use something like MODIS with 500 meter pixels. There's no river way up in a valley that's 500 meters wide, right? Maybe you go down to the Ganges, pretty far down, and you get this kind of really wide river that you can use MODIS data to study. But if we're talking about Himalayan rivers, then we need to use something much higher resolution. So for this, we're going to use Landsat data, the same data we used to look at the glacier lakes in the first exercise, which has a 30 meter pixel size, which is still too big for some very thin rivers way up high, but is quite good for the wider parts of many rivers, even in quite steep catchments. The idea is that we want to use the Landsat data to get river temperatures. So there's a thermal band on Landsat, which lets us get land surface temperature or water surface temperature. And we also want to get river color, which is a good proxy for sediment content, or at least turbidity, how much stuff is suspended in water. And you can use this to look for water quality, chlorophyll content, organic matter, these kind of things as well, not just for sediment content. So I've opened up my last notebook here, this exercise 5, and just like in the last exercise, I didn't have CartoPy installed, so I had to do this one extra little setup step to install CartoPy. This is what was suggested when the import didn't work. And then we load in the same packages as in the last one. We have our NumPy, our plotting, our GeoPandas for making these geographic maps, CartoPy for making our nice geographic maps, and then also this extra module which is used for converting GeoPandas data to Earth Engine data. And you can test again to just, well, actually I don't have this testing code, but I assume now that we've done this 5 or 6 times, we can all load in our Earth Engine data set and have this all set up. So when we want to work on these thin rivers, the first thing we have to do is figure out where those rivers are, right? It's not like we have a perfect data set or we have some label inside of our Landsat image that says this is a river and this is not a river. We have to decide where the river is and where we actually want to study the data. The two sort of main ways you can do this is to try to find a water mask grid. So you can look in each Landsat scene and try to classify it. Is this water? Is this not water? Or you can use some river network geometry. So if you have a shapefile that shows you where the rivers are as a line data set, something you might use in GIS, you can also say, okay, this is where my rivers are. Let's check the river temperatures at those points. So the two links I have in here, the first one is for an Earth Engine data set called the Global Surface Water Mapping Layers. And this is a data set that's based on Landsat. It's going from the 1980s up until 2022. And what it does is it uses Landsat data. So it has this 30 meter pixel resolution. And inside there is a few different values related to how often a certain area was covered with water. They've trained a really nice machine learning model on lots and lots of in-situ data to say this is water, this is not water. They sum them all up and they come up with something like a water occurrence. If you're in the middle of a lake, you should have 100% occurrence. It's always water. If you're in a channel that's moving around throughout the year or it's only flooded during part of the year, then you're going to have a lower surface water occurrence. And if you're always on the land, you're never wet, then you have 0. So we can use this to say, okay, we're only interested in places that have at least 50% water coverage or 25% water coverage. And those are the only areas that we want to focus on for our analysis. The other option is to use a geographic file, something like the hydro rivers data set, which gives us, I think they have a little map here when you open this up. But this is basically a vector file that looks something like this. You can get all of these different little lines, and then you can pull this into a GIS and figure out where all these lines are covering and say, I'm interested in this segment of this river. Let's check what the temperature looks like according to this location for my river. And this covers the whole globe from very big rivers to very small rivers. And it's based on topographic data, so elevation data. The sort of easier way to do this, staying within Earth Engine, is to just use our global surface water data set and look at this water occurrence and choose some water threshold. I'm only interested in areas that have at least 25% water coverage. You can make this more or less conservative depending on how many water pixels you're very interested in. Then I define a mask. I'm only looking for when my water occurrence is greater than my water threshold of 25. And now I have a water mask. And we can look at that if we run these two lines. Just like earlier, we're using GEE map. I've picked out a point that's, I think, somewhere in the middle of a river or nearby to a river. And what I'm visualizing here is from low to high colors. From blue is less frequent water cover, red is more frequent water cover. I'm doing my water threshold of 25 to 100% coverage. And I'm putting at the back a Google Maps, just so it's a little bit easier to see this against topography. And if I look at this, I can see that different parts of my river have different amounts of water occurrence. The red places are places where I have quite frequent water, and the blue places are maybe less frequently covered in water. Places where the water is quite shallow and there's a lot of sand during parts of the year, so maybe it doesn't always think that it has water. Versus some of the deeper areas, maybe I can turn this on and off. So if I go on my map here, I can turn off my layer and turn it on again, and I can see what some of these places that are always water, like, for example, a hydropower dam infrastructure, I think that's pretty much always water. Versus if I just go a little bit upstream, where the river gets a little thinner, it's not sure that this is always water. There's maybe a lot of dirt and stuff on the sides, so the water occurrence is less. But even with such an occurrence flag of about, here this is already 88%, right? So we're still talking about quite often water covered. These blue ones, I think, are a little bit lower. So now that we have some sort of idea of where our river is, the place that we want to analyze, we need to get some Landsat data. And we need to get temperature data and our water color data. So this is now a really long set of functions that is taking different kinds of Landsat data, Landsat 4, 5, 7, 8, and making it into one coherent kind of data set. It's renaming all of these different bands to blue, green, red, near-infrared, so on and so forth. It's checking these quality bands within Landsat, flagging out places that have clouds, or are in the shadows, or have snow and ice. We don't want to consider those for our river temperature, right? If it's snow covered, then it's definitely not open water. And then it's doing the same thing for Landsat 8 and 9, which have slightly different bands. And I'm getting all sorts of different data. So I'm getting every Landsat scene I can find. Landsat 5, Landsat 7, Landsat 8, Landsat 9, from some starting date of 1983 until an end date in 2026. This is even in the future. And all of this is just loading in and filtering the data. So we don't have to go through this line by line. This is taken from a couple of papers that were published, one by me, one by someone else. This is just the easy way to do this pre-processing to get to surface temperature data from Landsat. At the end, we end up with something that looks like this. So we have these different collections from Landsat 5, Landsat 7, Landsat 8, Landsat 9, and we can merge them all together, and now this collection has every single Landsat band that ever intersected our area, and that has water. So we're talking about quite a lot of images. We can actually run this and see what our size looks like. It might not even let us do this because it's quite a big collection, but we can test it. And see what it says. I think it's going to maybe time out or say it's too big of a collection to let us know, because I think this is thousands of images that it's trying to collect. Yeah, so we have more than 5,000 images. It ran out. Our user memory limit was exceeded. It doesn't know how to count so many Landsat images. Even if we can't count them directly, we can still operate on them. We can still select a single point and get the data out of those single points through time. To do this, we once again have our geometry. We can filter our data. So in this case, I'm getting from my full Landsat collection, I only want Landsat scenes that intersect my river point. And I only want data from March to April of 2024. So I'm looking for a very specific month, just so I can make a first plot and see what one individual Landsat scene looks like. And here, I'm visualizing not the bands 4, 5, 6, 7, not the Landsat data, but this surface temperature data, something that we've calculated from the Landsat scenes. So we can just do this to get an idea of what our surface temperature grid looks like for one Landsat scene. And so far, I haven't actually masked this to the river, so this should give us the temperature data over quite a large area, which is why it's going to take a few seconds to run here. So this is now covering our whole area. So it's one Landsat scene that covers quite a big region, but it's not yet masked out for the rivers. Where it is masked for is glaciers, snow, ice, if there's some cloud shadows in there, all of that is already removed. That was part of our pre-processing. So this Landsat collection that we have has some original or some initial filtering already done on it. But to focus just on the river, we need to use our water mask. And this is just setting these same parameters as before. I have my water threshold. I'm using that to select my water occurrence. I only want water occurrence greater than 25. And I am going to mask my full Landsat collection with my water mask. So now every single image in my Landsat collection should be masked to only using the water. And if I change this, the only thing I've changed in this next map is instead of full collection, I'm using water collection. This is the one that I just defined, masked to only the high water occurrence areas. And if we run this, it should hopefully run quite a lot faster since it has to show less data. And it should give us something that gives us water temperature only along the river. Maybe it also takes some seconds since it's still quite a lot of data. Let's see. Yeah. So now, this is the same area, and we can see that we only have values that are falling along this river. So we've done a quite quick filtering to have a grid of only our river temperatures. The other thing we wanted to add was this water color, so this turbidity data. And there's two different ratios I put in here. I put links for both of them. We can have a quick look. One is called the normalized difference turbidity index. So there's this normalized difference vegetation index, NDVI. There's also a normalized difference turbidity index, NDTI, which is just a measure of turbidity. It's how much stuff is suspended in the water. And it's based on the red and green data. So it's basically a difference between the red and the green bands. There's also been other publications which have, for example, looked at the ratio of near-infrared and red data to look at, for example, chlorophyll concentration. So this is another ratio that you can use to look at water quality or how much stuff is suspended in the water. And any of these ratios we can define, and we can do, for example, a normalized difference between our red and green bands, and that's how our NDTI is defined. And in this paper, this red near-infrared ratio, we can do the same thing. We can select our red band, divide it by our near-infrared band, and we call it red near-infrared. And we can add this function, this add turbidity data to everything in our water collection. So now we have also access to this turbidity data, which we can add as a map. So instead of, I'm doing everything the same here, but instead of visualizing surface temperature, I'm now visualizing my turbidity ratio, which should run also for a second here, and then we should get a map also of the differences in turbidity. So we can see that the differences maybe aren't as big as they were with the temperature data, but we can still go into any of these points and select any of them. If I can scroll here and get an idea of what this turbidity ratio is for this particular date. I think this also will tell me all the values of my other bands as well. Even though we're just visualizing one band, I think all the data is still there. Let's see. Yeah. So for any of these river points that we click, we can see that we have some normalized turbidity ratio, we have some red near-infrared ratio, we also have the values of all our different spectra, red, blue, green. We have our surface temperature of 23 degrees Celsius. So we can access all of this data from, for these specific river points. So just like we did in this last exercise, we can also use this kind of data to get an average, right? Even though this is much, much higher resolution, we can still clip it only to our Trishuli outline and get an average of our turbidity or an average of our surface water temperature through time. We're just relying on much more information than when we did the climate data. So once again, we can load in our Trishuli outline just like before, and we can filter our data to be only over, what do I have here? I have a 3-month window here from 2024 February until May. I'm getting the average turbidity. So this is now going to collect all of the Landsat scenes over Trishuli, calculate their turbidity, and calculate their temperature and all these things, and take an average. And we can then visualize our turbidity mean only over Trishuli over this 3-month period. And if we look around here in this map, this went quite quickly. And we can see that we have some parts of the river that are more or less turbid, depending on where you are. But you can also see that there's quite some gaps, right? There are places where the river was maybe too thin, you don't have enough data, maybe there was a lot of cloud cover in some of these places during these months. So the longer you do an average, the more complete your data is going to be. But then you're also averaging over a wider period, so you lose some of this temporal resolution. But even for loading, I think this is probably hundreds of Landsat scenes and doing some analysis and masking only to the river, this still takes 10 or 15 seconds to run, right? So we can get access to this data quite quickly. If you want to actually get these long-term means, so I'm setting up my export run, I'm filtering only to Trishuli, I want my surface temperature, and I want the long-term average. I'm not filtering the date anymore. I'm looking at hundreds or thousands of Landsat scenes. That is something that will never run during your computer or on your computer, especially at this 30-meter resolution. Shakil started running it, what, half an hour ago, and it's complete. What was our 20 minutes? Okay, so longer than we have today to run these, but we can take these really big averages, and I can just open one up in QGIS and we can have a look. I put them on GitHub so we could have a look at them together. Let's take this, for example, our water temperature, long-term average. And maybe I will also get this Trishuli outline here. And I can see if I change my color here, maybe we do something like this one. So blue will be my colder colors, and red will be my warmer colors. And I set this up like this, and it's a little bit hard to see at this scale. If I zoom in down at the bottom of Trishuli, I have warmer water. And if I go up to these higher elevation parts of the river, it's much cooler water, right? So exactly what we expect, especially in some of these very high areas like these glacier lakes that we looked at earlier this morning, right? They have very low average water temperatures. Whereas down here at the bottom, things are quite warm. Our average water temperature is 20 degrees or something throughout this long period of time. This includes the quite warm times of the year during the monsoon and also the cooler times during the winter and the fall. There's also in this, we won't run these because these probably take even longer to run. You can do the same kind of analysis we did before where you filter only to the 1990 to 2000 or 2010 to 2020. And you can look at these differences. So I can look at my difference in temperature, I can look at my difference in turbidity, and maybe I can, or I have a screenshot here. I can also just open this up. If I get out my Trishuli temperature, there we go, differences between 1990 and 2010. And we do a color map here. We can see that most places are warmer than they were before. So the blue stuff is everywhere that it's been warmer in 2010, and the red is where it's a little bit cooler. So this could be a channel that's migrated around a little bit. Mostly the sign is of warmer water over this 20 or 30 year period. And we can look even upstream. Some of the temperature trends are higher and lower. But this is quite a lot of data that is being analyzed, and we can just run it as short snippets of code like this, right? We have our whole filtered collection. We just select some dates, and we can export it and look at it just like we did before. And this is quite similar to the analysis that I did in a recent paper. The other approach, besides using this masking based on a grid, is to choose sample points. So go into our river network and pick out points that are along certain rivers and get the time series. Just like we got time series for one point location or for one area, we can sample different points of the river, so specific areas. And to do this, I have created a little filtered data set which covers part of the Trishuli. It should be different river points along here. Maybe I can also open it in QGIS, and we can have a look at it. Let's see, vector, Trishuli, river filtered. So this looks something like this. It's a really big collection of vertices from my river network. And you can see that it overlays quite well with my surface water mask. So these vertices are coming from an elevation data set, so a different kind of data. But when we have all these sample points, we can use any individual one of them to pull out the time series ourselves and do more complex analysis. So instead of just looking at the averages in 2000s and the averages in the 90s, we can do real fitting, and we can de-season our data, and we can do all sorts of other time series analysis, anything you would want to do with the raw data. So just to show what this might look like, first we're just going to set up our same export time series data, just like we did in the previous exercises. We're going to take one single point location. So if I go into my geo data frame, this GDF, this is this collection of all of the points in the Trishuli that we just plotted here. We can select only one point, so the first point in my data set, which has some UTM coordinates and then some latitude and longitude coordinates. And I can look, for example, what my x value is. I can look what my y value is. And those are the coordinates that I can use to create an Earth engine geometry. So I want my x value, my y value, and now I can convert from that set of points, or that single point, into something that Earth engine understands. And now that it's an Earth engine geometry, it's the exact same thing we've done in the last two exercises. We feed it in, we use this reducer, we get our time series of that single point location, and we can run this at two different buffers. I'm only selecting data from 2020 till 2025, only the areas that are nearby my point location. And when I'm exporting my time series data, I'm putting a buffer on my point. So if we look at any of these points, they don't always sit perfectly in the river, right? So maybe you want to be a little bit more robust and select a little circle around that. Maybe the river temperature in a 500-meter area is not changing that fast, right? Unless you have a new channel coming in, the water temperature as you go 1 kilometer straight upstream is not changing very much. So if you average the values of this whole set of pixels that are quite similar, you can fill in some of the gaps due to clouds. You can just get a more stable estimate of your temperature that's less prone to noise. So that's what this line is doing here. I set a buffer of 100 meters, so that would be a quite small buffer, and a buffer of 1,000 meters, so a little bit bigger. And these two things should look quite similar. They should be a similar size. You can see that when I do my bigger buffer, I get a few more data points. So we're including a few more data points that were missed due to cloud cover or something else in my small data set. But if I plot the two time series, they should look pretty similar. So when I include more data, I have some more values in there, but otherwise things look pretty similar, which is telling me that the area of 100 meters in the river and the area of 1,000 meters in the river, the temperature is pretty stable. So this is a decent way to average the data, get a few more data points, and even out a little bit of the noise. Does that make sense? Okay, good. We're almost there. So the second thing we can do is run the same code, but for now we're exporting this turbidity index. So I'm exporting this, this sediment content, and we can plot the same thing. This will take a second here, but we can see that the effect is pretty similar for the temperature or for this turbidity data. The turbidity data probably has more variability in it over a shorter period of time or a shorter distance. If you have sort of a bend in your river, you can go from clear water to quite dirty water very quickly. As the water speeds up, or it hits a lake, or it hits a dam, you can change your turbidity very fast over a short distance. Whereas if you have temperature, it's still pretty smooth. So this tells me that while the sort of average value of these two data sets is pretty similar, there's some big differences between the small and the bigger buffer. So it's a little bit more dangerous to use a big buffer for turbidity data than for temperature data, but for our purposes of just doing a little initial analysis, it's pretty okay. So the last thing I want to do here is just to make this a little bit clearer, is to focus on a smaller spatial area. So I found one area which is near a hydropower dam. You can see this is their storage pond here, and they have a dam here, and the river is quite a lot deeper and wider upstream versus downstream. And you can see that the river temperature changes a lot between these two things. When your river is slowing down and getting deeper, it's getting a lot cooler too, right? So there should be some gradient in our temperature due to hydropower dams. And that's exactly what I want to look at. I want to look at, for the same time periods, what's the temperature time series here, and what's the temperature time series here a little bit downstream. So what is the direct impact on the river of this hydropower dam? So for this, I chose two different points. I'm using a smaller buffer, 250 meters. Those are those 2 points that I circled on my image here, and I'm calling them above dam and below dam. So I get my turbidity time series above and my turbidity time series below. Same with the temperature, above and below. And this hopefully runs fairly quickly, and we can just make a plot with two charts. The top one will show turbidity, and the bottom will show temperature, and on each one there should be two lines. One is the time series above the dam, and one the time series below the dam. It's a lot slower to work with the Landsat data than the climate data, right? There's a lot more data involved when you use 30 meter data. Okay, there we go. So now on my charts here, I can see that there are some big differences, right? During some times of the year, the turbidity is basically the same. And some times of the year, there's these really big differences. Same with temperature. There's some times of the year, in the winter, for example, where the temperature is basically the same. And there's some times during the summer where the temperature is really, really different. So it depends on when they're storing water, when they're flushing water, when there's so much water coming down that they just let it all go and they're not stopping so much. And that will change what the difference between the upstream and downstream temperature and turbidity is throughout the year. Now that we have these time series, we can also look at this comparison, not just with the time series, but also we can look at these differences. And this is, I think, the last thing I want to show here is if I compare my difference in my turbidity and my temperature, so I subtract my upstream and my downstream, my upstream and my downstream, and I'm going to plot them based on the day of the year. We should see that at different times of the year, the relationship between the above and the downstream temperature and above and the downstream turbidity is quite different. So let's take a look at this. And we end up with something that looks like this. If we start, for example, with temperature, we see that in the spring, this temperature difference is really big as cold water collects in these ponds above the dam, and it gets a lot cooler than the water that's going downstream. And then during the summer, when they're getting tons and tons of water and they just have to let it all go straight out of the dam, the temperature differences are really small between the up and the downstream parts of the dam. Something a little bit similar happens with the turbidity. You get these big differences during the spring when the water is being trapped and the sediment is not allowed to go through to the lower part of the dam. And then right in the peak of the monsoon, it's pretty similar. But then again, there's this difference coming into the fall as again water starts to be trapped behind this dam. And this is the kind of detailed data that you would not be able to see from just looking at these averages or looking at these maps. You have to go in and select the 2 points that represent what you actually want to look at. What's the difference, or what's the impact of this particular hydropower dam, and how can I pull this out? And something like this, you can make the case that over a number of years, if I look here in the spring, I have a very, very pronounced difference in my water temperature due exactly to this hydropower dam. So that is it. That was my last piece of